Hello. Useful information about eigenvalues of a square matrix A is encoded in a special scalar equation called the characteristic equation of matrix A. Jumping right into an example, find the eigenvalues of matrix A, which is a 2 by 2 square matrix. Let's find all lambda such that A minus lambda times vector x is equal to 0, and again we got to make sure it has a non-trivial solution. So let's form A minus lambda times the identity. Here's matrix A, lambda times the identity. Those ones from the identity just become lambdas. Subtract based on position, 2 minus lambda, 3 minus 0, same. And then finally negative 6 minus lambda. The determinant, recall that the determinant of a 2 by 2 matrix is A times D minus B times C. So we're going to use that formula to take our determinant. So we have 2 minus lambda times negative 6 minus lambda, be careful to use parentheses, minus the other diagonal, 3 times 3. And we want this matrix to be not invertible. So what we're gonna do is we're gonna set this equal to 0. Determinant of our matrix, we're just gonna take this part and carry it down. I just recopied it right here. Okay, so FOIL the first two, negative 12 minus 2 lambda, positive 6 lambda, positive lambda squared minus 9. Combine like terms, we have lambda squared plus 4 lambda minus 21. This polynomial, your characteristic polynomial, can be factored using lambda plus 7 times lambda minus 3. 7 minus 3 is 4. 7 times negative 3 is negative 21. If you set each factor equal to 0, it would require a negative 7 to make this one 0, and 3 to make this factor 0. So your eigenvalues are negative 7 and 3. Recall, if you have to find the determinant of a 3 by 3 by hand, then I always use the first column unless it's just really unruly. So what I'm going to do is, remember these are called cofactors and you have minors. So I'm going to start in the top left, 2 times, if you ignore the first column and first row, then you have these 4 entries for your minor. Alternating signs, negative 4, so we're going to do minus 4, block out that column and row, and you'll have 3, 1, and 2, 1 for your co-minor entries. And then finally, so we go positive, negative, finally positive 0, times the determinant, and we'll leave off the bottom row and first column, these 4 entries, 3, 1, 0, negative 1. So there's a lot to keep up with, and the reason I want to encourage you to do it by hand is because later when we get into trying to do a 3 by 3 solving for the eigenvalues and characteristic equations, we're going to need to remember how to do it by hand. So let's go to it. We have 2 times the determinant, so that's 0 minus negative 2, minus 4 times the determinant, 3 times 1 minus 1 times 2, and then finally 0 times whatever that is just going to be 0. So we have 2 times positive 2, that's 4, minus 4 times 1, that's negative 4, and again the 0 trailing. we end up getting 0. A matrix A is invertible if and only if A times X equals 0 has the trivial solution. And that's where you would have a pivot in every column. If A is invertible, then 0 is not an eigenvalue, and the determinant of A is not 0. And that all ties in together, the invertible matrix theorem. Definition: the scalar equation, determinant of A minus lambda times the identity, is equal to 0. That's called the characteristic equation. A scalar lambda is an eigenvalue of a square n by n matrix if and only if lambda satisfies the characteristic equation given by determinant of A minus lambda I equals 0. So let's do an example. Find the characteristic equation and the eigenvalues of the matrix A. And again, this one's a 2 by 2 square matrix. First, let's form A minus lambda I, matrix A minus lambda times the identity matrix. Subtract based on position, negative 5 minus lambda, 1 minus 0, 3 minus 0, negative 1 minus lambda. Now, once you have that matrix formed, find the determinant. So that is going to be, remember, determinant, if DET is not written as a prefix, vertical bars mean the same thing. It's determinant. Either notation's fine. Multiply your main diagonal terms, negative 5 minus lambda times 1 minus lambda, minus, and then you multiply your other diagonal, 3 times 1. FOIL the first two, so we have positive 5, positive 5 lambda, positive 1 lambda, and finally positive lambda squared, minus 3. Combining like terms, we have lambda squared, 6 lambda, and finally 2 for our constant. That is called your characteristic polynomial. Lambda squared plus 6 lambda plus 2. The real eigenvalues are when this characteristic polynomial is set equal to 0, and that's called a characteristic equation. Now, if we set this equal to 0, we can't factor like we did on the previous problem. We can't get any integers to add up to 6 and multiply out to 2. Because with 2, all your options are 1 and 2. Now, if that's a 3, you can factor. Way back in the college algebra days, if you run into a quadratic that is set equal to 0, but you can't factor it, you can always fall back on quadratic equation. Okay, so that's minus b, and let's recall A is 1, b is 6, c is 2. So minus b plus or minus b squared minus 4ac, a is 1, c is 2, all over 2 times a, so that's 2 times 1. In the upper left, we have negative 6 plus or minus. Under the radical, that's 36 minus 8. 36 minus 8 is a total of 28. That's our determinant. And in the denominator, 2 times 1 is 2. Since square root of 28 can be broken down with a perfect square factor, you can rewrite 28 as 4 times 7. That'll simplify to 2 square root of 7. You can square root the perfect square and just leave the 7 underneath. That's what I've come up with here, 2 square root of 7. Since all three numbers not under the radical are even, you can have negative 3 plus or minus. That cancels to a 1, square root of 7. On your homework, there is a plus minus button, so you can just type this in and hit the plus minus in between. If you have to separate, just remember The first time it gets either the positive or the negative, and then the second time it just gets the one you didn't use the first time. So make sure there's a plus and a minus in the middle, and you'll be good to go. These are 2 eigenvalues for this original matrix. Let's repeat for a 3 by 3. Now the 3 by 3, it is a headache because there's so much tedious math to keep up with. So we have a 3 by 3 matrix. First thing we do is we're going to form, just like on the previous example, we're going to form A minus lambda I. So here's matrix A minus lambda times the 3 by 3 identity. We'll just put lambdas on the main diagonal, zeros everywhere else. Subtract based on location, 1 minus lambda, 3 minus lambda, 0 minus lambda, and then all the other entries will stay the same because we have a whole slew of zeros in that identity matrix. After you have formed A minus lambda I, take the determinant. Again, DET as a prefix is fine. Vertical bars represent the same thing. Now we did a 3 by 3 determinant a slide or two ago, so we've got to be very careful. It's very meticulous. Again, I'm going to go down the first column, so I'm going to take 1 minus lambda, ignoring the first row, first column. My minor are these 4 entries, and I carefully copied those. Minus 4, ignore that row and column. 0, negative 1, 6 minus lambda are the remaining 4 terms for that minor. And then finally, plus 0. If you cross out the first column, first column, third row, these 4 terms are remaining. And I slip those in here. So it's positive, negative, positive. 1 minus lambda times the determinant. So I put 1 minus lambda. I put a bracket because we need to multiply these two. 3 minus lambda times negative lambda minus this diagonal multiplied, 6 times negative 3. Okay, so that closes off the first. The second part, negative 4. And then the second matrix determinant is 0 minus negative 6. Third part, we have a 0 here, so it doesn't matter what the determinant is. All that's going to just turn into a 0. 1 minus lambda, I brought it down. Distribute negative 3 lambda plus lambda squared, positive 18. And then negative 4, 0, plus 6, and then plus 0. Okay, so finally we're getting closer. I just rearranged these terms in descending order. Lambda squared minus 3 lambda plus 18. Clean this up, that's just a negative 24. Multiply 1 all the way through, that's lambda squared minus 3 lambda plus 18. And then multiply through or distribute a negative lambda cubed, positive 3 lambda squared, minus 18 lambda, and then minus 24. Arranging all these terms in descending order and combining like terms, we have a negative lambda cubed. There are 2 lambda squareds, a 1 and a 3, so that totals out to 4 lambda squared. 2 terms with a lambda, negative 3 minus 18, that totals negative 21 lambda. And then finally a couple of constants, 18 minus 24 is negative 6. That's your characteristic polynomial. Theorem: if matrix A is triangular, then determinant of A is the product of the entries on the main diagonal. We discussed this earlier where we had a triangle of zeros. If it's in triangular form, then your determinant is just the product of the main diagonals. Our problem is we're having to find characteristic equations, so that involves lambda, and we just can't go straight through with multiplication because the eigenvalues are whatever we get for lambda. But anyway, to make a long story short, when you have a triangular matrix, the main diagonal is going to be these entries minus lambda. Original entries minus lambda. The rest of these will stay the same. All these zeros stay the same, and the terms not on the main diagonal will stay the same. Determinant is the product of the entries on the main diagonal. So down here I've got 5 minus lambda times 3 minus lambda times another 5 minus lambda, and multiplied by 1 minus lambda. That's why these four factors are all written out. I just took them in order down the main diagonal, writing them out. 5 minus lambda appears twice, so I wrote it once, gave it a power of 2. Don't worry about trying to multiply all this out. If you were to multiply all these out, you would get a horrendous equation to work with. It's easier on the higher ordered ones, the higher powered ones, because there's 4 lambdas. It's easier to leave it in factored form. I'm going to write 5 minus lambda. It's got a multiplicity of 2 because that shows up twice. 3 minus lambda and 1 minus lambda only show up once, so there's multiplicity 1. Taking the first factor, 5 minus lambda squared, if you square root both sides, you get 5 minus lambda equals 0. Solving for lambda, you get 5. This eigenvalue has a multiplicity of 2 because it came from a factor with a power of 2. 3 minus lambda is equal to 0 if lambda is 3, and 1 minus lambda is equal to 0 if lambda is 1. The last two, the eigenvalues of 3 and 1, have a multiplicity of 1, and the eigenvalue of 5 has a multiplicity of 2. Now, go back to the top and look at your main diagonal of A. A couple 5s, a 3, and a 1. A couple of 5s, and a 3 and a 1. Let me know if you guys have any issues with your homework. I tried to make sure I tackled an example of each in this video, so let me know if you have any questions come up. Don't forget, in addition to the YouTube videos, you can also go into Google Drive, and the documents in Google Drive are titled the same as they are in your homework. And just let me know if you have any questions. I appreciate you guys.